For more than half a century, modern physics has been built on the assumption that reality is internally consistent, that its rules may be incomplete, but they do not contradict themselves. The equations may be difficult, the experiments expensive, but the foundation is supposed to hold. What has changed in the last few years is not philosophy, and not interpretation, but measurement. Precision instruments have begun to report numbers that do not fit inside the framework we rely on. Not dramatic deviations, not spectacular failures, but small, stubborn mismatches that refuse to go away. And in physics, small mismatches are often the most dangerous kind. The reason is simple. The closer a theory comes to perfection, the less room there is for error. When a prediction is precise to many decimal places, even a tiny deviation implies that something fundamental has been left out. These are not cracks you can paper over with better language or improved statistics. They point to missing structure, missing forces, missing assumptions about how reality is put together. The story begins in the most controlled environments humanity has ever built. Particle accelerators designed to test the deepest rules of matter by smashing it apart and weighing the pieces. For decades, these machines have confirmed the same picture again and again. The masses line up. The symmetries hold. The bookkeeping balances. But recently, one number did not land where it was supposed to. And the consequences of that misplaced number reach far beyond particle physics. Because when a fundamental particle comes out heavier than it should be, it does not just suggest a calibration problem. It suggests that the vacuum itself is not empty in the way we thought. That unseen influences are leaning on the structure of space. And once that possibility is allowed, a chain reaction begins. Questions about stability, about gravity, about dimensions, about time itself stop being abstract and start becoming unavoidable. What follows is not a collection of disconnected mysteries. Each problem feeds directly into the next. A measurement forces a correction. The correction destabilizes a field. The unstable field exposes a deeper inconsistency. And taken together, they point toward a picture of reality that is far less solid than it appears. A reality that may be balanced on a narrow mathematical ledge, held together by constraints we do not fully understand, and vulnerable to failures that would arrive without warning. We start with the rulebook that was supposed to be final. The framework that tells stars how to burn, atoms how to bind, and particles how much they are allowed to weigh. Because the first crack does not appear at the edge of the universe. It appears in the heart of the equations themselves. The framework is called the Standard Model of Particle Physics. It is not a philosophy, and it is not a guess. It is a tightly constrained mathematical structure that specifies which particles are allowed to exist, how they interact, and what numerical values their properties must take. It has survived every experimental test thrown at it for more than 50 years. When a new particle is discovered, its behavior fits the equations. When a decay is measured, the probabilities line up. In practical terms, it is the most accurate description of nature ever constructed. What makes the standard model fragile is not that it fails often, but that it fails almost nowhere. Its predictions are so specific that many quantities are fixed to within fractions of a percent. There is no flexibility. If a particle weighs more or less than the value demanded by the equations, the symmetry of the theory breaks. Forces stop cancelling the way they should. Calculations that once converged begin to diverge. A single wrong number can destabilize the entire structure. One of the most tightly constrained pieces of this framework is the particle responsible for the weak nuclear force. This force governs radioactive decay and plays a critical role in nuclear fusion. Without it, stars would not burn steadily, and the elements heavier than hydrogen would never form. The particle that carries this force has a mass that is not arbitrary. It is locked in place by the geometry of the theory. Change that mass, even slightly, and the internal balance of the model shifts. For years, experimental results matched the predicted value closely enough that any discrepancy could be dismissed as noise. But as detectors improved and datasets grew larger, the tolerance for uncertainty collapsed. The error bars shrank. And when the measurements were repeated with enough precision, the number did not drift toward the expected value. It settled somewhere else. That difference was small, less than 1%. But it was consistent. And consistency is what makes a deviation dangerous. Random error averages out. Systematic disagreement does not. When trillions of particle collisions are analyzed independently and the same excess appears, the conclusion is no longer statistical. It is structural. This is the point where particle physics stops being about particles. Because a mass that is too heavy cannot be explained in isolation. It implies that something unseen is contributing energy. Something interacting with the particle through the vacuum itself. And that shifts the problem from the properties of matter to the nature of empty space. The vacuum in modern physics is not a passive backdrop. It is an active medium defined by fields that permeate all of space. Particles acquire mass by interacting with these fields. Forces emerge from their structure. If a particle appears heavier than allowed, the most direct explanation is that the vacuum is behaving differently than expected, that the ground state of reality is under stress. Once that possibility is admitted, the question is no longer whether a single particle is misbehaving. The question becomes whether the vacuum itself is stable. If the vacuum is unstable, that instability does not announce itself with noise or motion. It hides in the background values of fields that appear constant. For decades, physicists assumed that the universe sat in the lowest possible energy state, a true vacuum, a configuration that could not decay into anything simpler. That assumption was not aesthetic. It was necessary. A universe resting anywhere else would be temporary by definition. But the mathematics of quantum field theory never actually guaranteed that we were in the lowest state. It only described the state we occupy now. When the measured particle masses are plugged back into the equations, especially the mass of the weak force carrier and the scalar field that gives particles their weight, the shape of the vacuum energy landscape changes. The smooth valley that once implied absolute stability becomes a shallow shelf. This shelf is not hypothetical. It is a direct consequence of measured numbers. The equations describe an energy barrier separating our current vacuum from a lower one. On one side of the barrier, the laws of physics look the way they do now. On the other side, the values of fundamental constants shift. Particle masses change. Forces rebalance. Chemistry as we know it may not be possible at all. In classical physics, a system sitting behind an energy barrier is safe unless something pushes it over. A ball at the bottom of a bowl stays there until an external force acts on it. But the vacuum is not classical. It is governed by quantum mechanics. And quantum systems do not require a push. They exploit probability. Quantum tunneling allows a system to cross an energy barrier without ever climbing over it. The system does not pass through intermediate states. It simply appears on the other side. This behavior has been measured countless times in laboratories, from radioactive decay to semiconductor electronics. It is not controversial. It is built into the equations. Applied to the vacuum itself, tunneling becomes far more serious. The vacuum is a field that exists everywhere at once. If even the single point in space were to tunnel into the lower energy state, it would not remain isolated. That point would become the seed of a new phase of reality. The transition would take the form of a rapidly expanding bubble. Inside the bubble, the vacuum would be in the lower energy configuration. Outside it, the universe would remain unchanged. The boundary between the two would move outward, driven by the energy difference between the states. And because nothing in the equations limits this expansion below the speed of light, the boundary would accelerate until it reached that limit. This is not an explosion. There is no shock wave, no radiation front, no advanced signal. The laws of physics inside the bubble are different, but the transition itself carries no information ahead of it. Light cannot outrun it. There is no warning mechanism built into the universe. If such a transition occurred anywhere within the observable universe, the effects would be instantaneous from the perspective of anything in its path. Atoms would not burn or tear apart in stages. The rules that define atomic structure would simply change. Bound states that are stable now would no longer be allowed. Matter would not be destroyed in the usual sense. It would become undefined. The unsettling part of this scenario is not that it predicts an imminent event. The calculated lifetime of the current vacuum, using known parameters, is vastly longer than the age of the universe. But that estimate depends on the assumption that no unknown physics modifies the energy landscape. And the very anomaly that triggered this chain of reasoning suggests that unknown physics is already present. A particle that is heavier than it should be implies additional contributions to the vacuum energy. Those contributions reshape the barrier. They can lower it, thin it, or destabilize it entirely. Even small changes in these parameters can alter decay probabilities by orders of magnitude. This sensitivity is what makes the problem unavoidable. At this point, the issue stops being about catastrophe and becomes about consistency. A stable universe should not require such delicate balancing. A vacuum that exists only because multiple large effects cancel each other almost perfectly is not robust. It is tuned, and tuning without a mechanism is a warning sign in physics. The vacuum instability problem does not exist in isolation. It intersects directly with another discrepancy that has troubled physicists for decades. When the energy of empty space is calculated using quantum field theory, the result is not small. It is enormous. Every fluctuating field contributes. Every virtual particle adds energy. When summed, the predicted density is so large that space-time should curl in on itself instantly. But it does not. The observed energy density of empty space, inferred from the expansion of the universe, is tiny. The difference between the predicted value and the measured one is not a rounding error. It is the largest mismatch ever encountered in science. A discrepancy of 1 part in 10 to the power of 120. This is not a problem of calculation. The methods are sound. The inputs are known. The failure lies in the assumption that the vacuum energy contributions add up straightforwardly. Something is cancelling them. Something is enforcing an almost perfect balance. The instability suggested by particle mass measurements and the near cancellation implied by cosmology are two sides of the same issue. The vacuum appears to be both delicately balanced and structurally stressed. That combination is not what a fundamental ground state should look like. And once again, the implications extend beyond empty space, because the same imbalance that destabilizes the vacuum also appears in the relative strength of the fundamental forces. Gravity, in particular, stands out. Compared to electromagnetism, it is absurdly weak. So weak that it is difficult to treat as a peer at all. If gravity were simply another force operating within the same framework as the others, Its weakness would require explanation. And the most direct explanation is that gravity is not fully confined to the universe we experience. That part of its influence is leaking away. This is where the cracks stop being local and start becoming geometric. Because a force that weak does not just suggest missing particles. It suggests missing dimensions. Gravity's weakness is not subtle. Compared to the electromagnetic force, which binds electrons to nuclei and allows atoms to exist at all, gravity is weaker by a factor so large that it barely fits inside intuition. A small refrigerator magnet can overcome the gravitational pull of the entire planet. This is not a coincidence, and it is not a matter of scale. It is a numerical relationship built into the equations, and it should not exist. In the early universe, all fundamental forces are expected to emerge from a common origin. They should be comparable in strength. Instead, gravity appears diluted, as if most of it has gone missing. Physicists call this the hierarchy problem. It is not a philosophical discomfort. It is a structural contradiction. If gravity truly operates within the same dimensional space as the other forces, then its extreme weakness has no natural explanation. The equations allow it, but they do not justify it. The only explanations that work require gravity to behave differently from everything else. Not weaker at its source, but weaker where we experience it. One way to weaken a force without changing its intrinsic strength is to allow it to spread out. If gravity is not confined to the same dimensions as matter and light, then its influence would be diluted across a larger volume. The more dimensions it can access, the less concentrated it becomes in the ones we occupy. To an observer limited to 3 spatial dimensions, gravity would appear feeble, even if it were strong in the full geometry. This idea forces a rethinking of what the universe is made of. Instead of a self-contained 3-dimensional space, reality becomes a layered structure. Matter and radiation are confined to a lower dimensional surface, while gravity is free to move through additional spatial dimensions that remain hidden from direct observation. These dimensions are not necessarily large. They could be compact, curled up at scales too small to detect directly, or extended but inaccessible to anything except gravity. This is not speculation disconnected from experiment. If gravity can move into extra dimensions, then energy can leak out of the observable universe during high-energy particle collisions. The total energy before and after such a collision should balance exactly. That balance is one of the most fundamental conservation laws in physics. If energy appears to vanish, it must have gone somewhere. Particle accelerators are designed to test this principle with extreme precision. Every collision is measured in detail. Every particle that emerges is tracked. The energy budget is carefully reconstructed. Most of the time, nothing is missing. But physicists are not interested in the typical events. They are hunting for the rare ones where the accounting does not close. If a collision produces a particle that can escape into higher dimensions, the detectors will register an energy deficit. Not because the energy is destroyed, but because it leaves the accessible space. This deficit has a specific signature. It does not radiate outward symmetrically. It vanishes along a direction the detectors cannot see. This pattern is called missing transverse energy, and it is one of the clearest experimental tests of extra-dimensional theories. So far, no unambiguous signal has been found, but the absence of evidence has narrowed the possibilities rather than eliminating them. The scales involved are higher than current machines can fully probe, and the same measurements that fail to reveal extra dimensions continue to reinforce the original problem. Gravity remains anomalously weak. The hierarchy remains unexplained. What makes this situation more unsettling is that the missing energy problem does not appear only in gravity. The universe itself seems to be missing mass. When astronomers measure how galaxies rotate, the visible matter is not enough to hold them together. Stars orbit too fast. Galaxies should tear themselves apart. They do not. Something unseen provides the additional gravitational pull. This discrepancy is not local. It appears in galaxy clusters, in gravitational lensing, and in the large-scale structure of the universe. The simplest explanation is the existence of an invisible form of matter that interacts gravitationally but not electromagnetically. For decades, this idea has guided experimental searches. Detectors have been built deep underground. Telescopes have been pointed at the sky. Yet no direct detection has occurred. The continued absence of a dark matter particle does not disprove its existence. But it does open the door to alternative explanations. One of them follows naturally from the same framework used to address gravity's weakness. If gravity can propagate through extra dimensions, then gravitational influence does not have to originate within our universe. Mass in a nearby dimensional layer could exert force without emitting light or interacting directly with matter. In this picture, the unseen mass shaping galaxies is not composed of new particles filling our space. It is the gravitational shadow of matter located elsewhere. The effect would be indistinguishable from dark matter using gravitational measurements alone. But it would explain why decades of particle searches have come up empty. There is nothing here to find. This possibility ties the hierarchy problem, vacuum instability, and missing mass into a single geometric framework. The universe becomes a thin region embedded in a larger structure. Forces behave differently depending on how they interact with that structure. Stability becomes a local property, not a global one. And once reality is no longer self-contained, motion itself takes on a different meaning. On the largest scales, the universe is expected to expand uniformly. Galaxies should drift apart in all directions, with no preferred flow. But measurements of galaxy clusters reveal a subtle deviation. Instead of moving randomly with expansion, large regions of the universe appear to be drifting together in a common direction. This motion cannot be explained by known structures alone. The gravitational pull required exceeds what can be accounted for by visible matter and even by conventional dark matter models. The implication is uncomfortable. The source of the pull may lie beyond the observable universe, beyond the region light has had time to reach. If the universe is embedded in a larger space, then large-scale motion may reflect gradients in that space. Our observable region could be sliding along a slope defined by mass or geometry outside our horizon. In that case, the expansion we observe is not the whole story. It is layered on top of a deeper flow. At this stage, the cracks are no longer confined to particle physics or cosmology alone. They intersect. Measurements at the smallest scales hint at missing structure. Observations at the largest scales point toward external influence. And between them sits gravity, behaving as if it is not entirely at home. To understand whether this picture is coherent, physics turns to the most extreme objects known. Objects where gravity dominates completely. Objects where information, energy, and geometry are pushed to their limits. Because if reality is fragile, the fault lines should be clearest where the strain is highest. That brings the story to black holes. Black holes are not exotic outliers. They are unavoidable predictions of general relativity. Whenever enough mass is compressed into a small enough region, space-time collapses inward and forms a boundary beyond which information cannot escape. That boundary is called the event horizon. Once something crosses it, there is no signal that can return. From the outside, the object appears frozen. From the inside, physics, as we understand it, breaks down. For a long time, black holes were treated as mathematical curiosities. perfect absorbers that swallowed matter and stored it forever. But that picture changed when quantum mechanics was applied to the horizon itself. When quantum fields are placed in curved space-time, the vacuum near the horizon becomes unstable. Particle pairs form spontaneously. One falls inward. The other escapes. To an outside observer, the black hole emits radiation. This process, now called Hawking radiation, has a precise temperature and a precise energy spectrum. And over extremely long timescales, it causes black holes to lose mass and eventually evaporate completely. This discovery solved one problem and created a deeper one. Because the radiation carries no information about what fell in. It is thermal, random, featureless. If a black hole can form from matter with a detailed internal structure, and then evaporate into radiation that contains none of that structure, information has been destroyed, not hidden, not scrambled, gone. That outcome is forbidden by the fundamental rules of quantum mechanics. Information loss would mean that the future cannot be uniquely determined by the past. The universe would cease to be predictive. This contradiction is known as the black hole information paradox. It is not a technical puzzle. It is a direct conflict between the two pillars of modern physics. Either quantum mechanics is wrong, or our understanding of gravity is incomplete. There is no third option. Attempts to resolve this paradox forced physicists to rethink where information actually resides. The intuitive answer, that it lives inside the black hole, leads directly to loss. The alternative is that information never truly enters. That when matter approaches the horizon, its quantum state is imprinted on the surface instead. This idea sounds artificial until the mathematics is followed through. The entropy of a black hole, which measures how much information it can store, does not scale with its volume. It scales with the area of its event horizon. Every increase in surface area corresponds to a fixed increase in entropy. The interior does not contribute. Only the boundary matters. This result is exact. It is not approximate, and it is not model-dependent. It suggests that the maximum amount of information contained within a region of space is determined by the area enclosing it, not the space inside. That observation is deeply counterintuitive. In everyday experience, storage capacity grows with volume. In gravity, it does not. The implication is that the three-dimensional interior of a black hole is not fundamental. It is a derived description. The true degrees of freedom live on a two-dimensional surface. The interior behaves like a projection, a hologram. Once this principle is accepted for black holes, it becomes difficult to justify restricting it to them alone. A black hole is not a special object in isolation. It is a region of space-time governed entirely by gravity. If gravity enforces surface-based information limits in one context, it likely does so everywhere. This line of reasoning leads to the holographic principle, the proposal that the information describing a volume of space can be encoded on its boundary. The familiar three-dimensional world becomes an emergent description, a reconstruction, not the underlying reality. This is not philosophy. It is supported by exact mathematical correspondences. Certain theories of gravity in higher dimensional spaces have been shown to be equivalent to non-gravitational theories defined on their boundaries. Every process in the volume has a one-to-one translation on the surface. Nothing is lost. Nothing is added. The descriptions are interchangeable. In this framework, space itself is no longer fundamental. Distance, volume, and geometry emerge from more basic ingredients. And those ingredients are informational. If space is emergent, it raises an immediate question. What holds it together? Why does the geometry appear smooth and continuous instead of fragmenting into disconnected pieces? The answer that has gained the most traction does not involve force or matter. It involves correlation. Quantum entanglement links the states of particles so that they cannot be described independently. Measurements on one influence predictions about the other regardless of separation. For a long time, this was treated as a strange but isolated feature of quantum theory, something that happened inside space-time. Recent work suggests the opposite. That entanglement is what creates space-time. That the connectivity of space is a reflection of the pattern of quantum correlations between underlying degrees of freedom. Where entanglement is dense, space is continuous. Where it weakens, geometry stretches. Where it vanishes, space disconnects. In this view, gravity is not a force pulling objects together. It is a manifestation of how information is distributed. Mass increases entanglement. Increased entanglement alters geometry. Objects follow the resulting curves because there is no other path available. This interpretation unifies several previously unrelated ideas. The weakness of gravity follows naturally. It is not mediated by a particle in the usual sense. It reflects a collective statistical property of quantum states. The surface scaling of entropy becomes expected. Information density controls geometry. But it also introduces a new kind of fragility. If space-time is built from entanglement, then disrupting those correlations would not just move matter. It would alter the existence of space itself. The vacuum would not be a stage. It would be a structure under constant maintenance. This brings the discussion back to instability. Quantum state collapse is no longer just a transition between energy states. It is a failure of the informational network that supports geometry. A region that tunnels into a lower vacuum does not merely change its constants. It loses the pattern of correlations that define the space around it. In that scenario, the expanding bubble is not invading existing space. It is replacing it. The boundary marks the edge between one informational regime and another. From inside the bubble, the previous universe does not exist. Not because it was destroyed, but because it was never part of the new description. At this point, time itself becomes suspect. If space emerges from correlations, time may do the same. The fundamental equations of physics do not single out a direction for time. They work equally well forwards and backwards. The apparent flow from past to future arises from boundary conditions, not from the laws themselves. Experiments in quantum optics have demonstrated that the ordering of events is not always fixed. Under carefully controlled conditions, outcomes depend on choices made after the relevant interactions have already occurred. These results do not allow signals to be sent into the past, but they do undermine the assumption that cause must always precede effect in a simple way. The most economical interpretation is that the universe does not evolve moment by moment. Instead, it exists as a complete four-dimensional structure. Past, present, and future are all equally real. The sensation of time passing is a feature of consciousness moving through this structure, not of the structure itself. This picture is known as the block universe. It removes becoming from the fundamental description of reality. Nothing comes into existence. Nothing leaves. All events simply are. When this idea is combined with quantum correlations and holographic encoding, a consistent but unsettling image emerges. Reality is a fixed informational object. Space and time are derived coordinates. Stability depends on delicate cancellations and correlations. And the anomalies that initiated this discussion are no longer isolated curiosities. They are symptoms. a particle that weighs too much, a vacuum that balances on a knife edge, a force that leaks away, geometry that depends on information. Each one alone could be dismissed. Together, they describe a universe that is not grounded in anything solid beneath it. The cracks do not mean that reality is about to fail. They mean that reality is not what it appears to be, and that the deeper structure supporting it is stranger, thinner, and more constrained than intuition allows. What remains is not fear, but limitation. A recognition that the world we experience is a stable configuration, but not a fundamental one. It exists because the numbers align, because correlations hold, because boundaries enforce rules. And if those rules change, reality does not collapse dramatically. It simply rewrites itself. That is the crack that matters. The question that remains is whether these cracks are purely theoretical, or whether they leave fingerprints that can be tested. Physics only advances when abstract structure is forced to confront measurement. And even here, at the deepest level of description, that confrontation has already begun. One of the most revealing places to look is not at matter, but at nothing. At the behavior of empty space under extreme conditions. In ordinary circumstances, the vacuum appears inert. But when space-time is curved, accelerated, or stretched, the vacuum responds. It produces particles. It stores entropy. It behaves like a physical system with degrees of freedom. This behavior is not optional. It follows directly from quantum field theory. When observers accelerate, they detect radiation where inertial observers see none. When horizons form, entropy appears. These effects imply that the vacuum is observer-dependent. Different frames assign different physical content to the same region of space-time. That alone is a warning. Fundamental reality should not depend on perspective, yet here it does. This observer dependence becomes extreme near horizons. Not just black hole horizons, but cosmological ones. The expanding universe creates a boundary beyond which information can never reach us. That boundary has a temperature. It has entropy, and it behaves mathematically like the event horizon of a black hole. This symmetry is not superficial. It suggests that horizons, wherever they appear, encode information and regulate what counts as physical. If the observable universe has a horizon with thermodynamic properties, then it too may obey holographic limits. The total amount of information accessible to us is finite. Not because the universe is small, but because access is constrained. There is a maximum number of bits that can be encoded within our cosmological boundary. This bound is not a conjecture. It follows from the same reasoning that governs black holes. This introduces an uncomfortable implication. If the universe has a finite information capacity, then it cannot support arbitrarily fine detail. There must be a smallest unit of description, a resolution limit beyond which distinctions are meaningless. In physics, this limit appears as the Planck scale. Below this scale, space cannot be subdivided further without losing coherence. Distances cease to be well defined. Geometry dissolves. This discreteness is not built into space-time by hand. It emerges from the requirement that information be finite. If a region could contain infinite information, horizons would violate thermodynamics. The fact that they do not means that the universe is, at its core, digital in structure, even if it appears continuous at large scales. Digital structure requires error control. Any system built from discrete units and subject to noise must correct mistakes or degrade over time. In engineered systems, error correction is explicit. Redundancy is added. Parity checks are performed. In physical systems, the assumption has always been that the laws themselves are exact and need no correction. But that assumption may be wrong. Certain formulations of fundamental physics contain structures identical to error-correcting codes. These structures are not added for convenience. They emerge naturally from the consistency conditions of the theory. They are required to preserve unitarity and locality under extreme conditions. Their presence suggests that the universe protects information actively, not passively. This is not evidence of intention. It is evidence of constraint. A system capable of sustaining stable complexity over long timescales must suppress noise. Otherwise, correlations decay. Geometry phase. The fact that the universe remains coherent over billions of years implies that such suppression exists. When this idea is combined with holography, a striking picture forms. The boundary encodes information redundantly. The interior reconstructed approximately. Errors in one representation can be corrected by reference to another. This redundancy is what allows space to appear smooth, even though it is built from discrete elements. It is what allows causality to emerge, even though time is symmetric at the fundamental level. But redundancy also implies non-uniqueness. There is more than one way to encode the same reality. Different descriptions can coexist without contradiction. This is why gravity can be described as geometry in one language and as entanglement in another. Neither is more fundamental. They are dual. Duality resolves many apparent paradoxes, but it also undermines intuitive realism. If the same physical content can be mapped onto radically different mathematical structures, then the question of what is really there loses meaning. Reality becomes relational, defined by consistency, not substance. At this point, the original anomaly that triggered this chain of reasoning comes back into focus. A particle with the wrong mass is not just a local problem. It is a sign that the mapping between description and reality is strained, that the parameters we measure sit at the edge of consistency, that the vacuum we inhabit is allowed, but not natural. Naturalness in physics is not aesthetic. It is a statistical expectation. Parameters should not require extreme fine-tuning unless protected by symmetry or mechanism. The values we observe do not appear protected. They appear balanced. And balance without explanation is instability, waiting to be exposed. The deeper issue is not whether reality will fail, but whether it can be derived uniquely from first principles. A theory that requires dozens of inputs to be measured rather than predicted is not complete. It is effective. It works within a limited domain. Beyond that domain, it must give way to something more constrained. The cracks identified here all point toward the same conclusion. The fundamental description of reality is not one of particles moving through space over time. That picture is emergent, useful, but not primary. Beneath it lies a structure built from information, correlation, and boundary conditions. A structure that permits the world we see, but does not guarantee it. Stability, in this context, is not absolute. It is conditional. It depends on relationships holding within allowed tolerances. It depends on cancellations remaining intact. It depends on no forbidden transitions occurring. This is not how classical reality behaves. It is how engineered systems behave. Engineered systems can be stable for long periods. They can appear robust, but they fail when assumptions break, not gradually, but abruptly, when redundancy is exhausted, when correction mechanisms are overwhelmed, when boundaries are crossed. Physics does not say that such a failure is imminent. It says only that it is not forbidden, and that distinction matters. A universe that forbids its own decay is fundamentally different from one that merely delays it. The unsettling part is not the possibility of collapse. It is the implication that reality does not rest on an immutable foundation. It rests on a set of constraints that happen to be satisfied here and now. Constraints that may not hold universally. Constraints that may not hold forever. The cracks, taken together, do not unravel reality. They reveal its architecture. They show that what feels solid is supported by structure that is abstract, relational, and fragile in ways intuition does not capture. That is not a reason for alarm. It is a reason for humility. Because it means that the world we experience is not the base layer of existence. It is a consistent solution to deeper rules. And consistent solutions, no matter how long-lived, are not the same as necessity. Reality holds together because it can, not because it must. What this leaves us with is not a mystery in the usual sense, but a boundary. A point beyond which the language we use stops lining up cleanly with what is measured. Physics has reached this point before. It happened when classical mechanics gave way to relativity. It happened again when determinism gave way to quantum mechanics. Each time, the mistake was assuming that familiar concepts were fundamental, rather than approximate. Space once seemed absolute. Time once seemed universal. Both turned out to be relational. The same process appears to be happening again. Matter, forces, and even causality are beginning to look like emergent features rather than primitives. The equations still work. The predictions still land. But the interpretation shifts underneath them. This shift explains why progress feels slow despite enormous technical advances. We are no longer refining a picture. We are circling the limits of one. Adding precision reveals tension rather than clarity. Each new decimal place tightens constraints instead of relaxing them. The more accurately we measure reality, the less comfortable our explanations become. This discomfort is not a failure of imagination. It is a sign that the underlying structure does not map cleanly onto human intuition. A universe built from fields, probabilities, and information was already difficult to accept. A universe where even those concepts are secondary is harder still. What physics is converging on is a framework where consistency matters more than substance, where laws are not enforced by mechanism, but by mathematical compatibility. Certain configurations are allowed, others are not. The universe exists in one of the allowed regions, not because it was chosen, but because it satisfies the constraints. In that sense, reality is closer to a solution than an object. It is what remains when all contradictions are removed. That solution can be stable for long periods. It can support complexity. It can even give rise to observers capable of questioning it. But it is not guaranteed. It is not protected by necessity. The cracks we have traced do not indicate that reality is about to fail. They indicate that it is conditional, that it relies on balances that could, in principle, shift, that its persistence is a fact to be explained, not a given to be assumed. This perspective reframes many long-standing questions. Instead of asking why the universe exists, the more precise question becomes why this configuration persists. Instead of asking what reality is made of, the better question becomes what constraints define it. Instead of asking how stable the universe is, the relevant question becomes what kind of stability it possesses. A classical system is stable because forces cancel. A quantum system is stable because transitions are suppressed. An informational system is stable because errors are corrected. The universe appears to borrow from all three categories. It behaves classically at large scales, quantum mechanically at small ones, and informationally at the deepest level we can probe. That hybrid nature explains both its robustness and its fragility. It can absorb disturbances. It can evolve without collapsing. But it cannot tolerate arbitrary change. There are forbidden moves, forbidden values, forbidden transitions. And when measurements begin to brush against those boundaries, the theory strains. This is why anomalies matter. Not because they predict disaster, but because they mark edges. They tell us where our descriptions stop being natural and start being forced, where parameters must be fine-tuned, where cancellations must be exact, where explanations become ad hoc. The weight of a particle, the value of a field, the weakness of a force, the smoothness of space. Each one, taken alone, can be rationalized. Taken together, they outline a narrow corridor through which reality must pass. A corridor defined by mathematics, not convenience. Whether there is something beyond that corridor is an open question. Whether the constraints themselves emerge from deeper ones is unknown. What is clear is that the universe we inhabit is not arbitrary, but neither is it inevitable. It sits between those extremes, supported by structure we are only beginning to glimpse. The idea that reality could unravel is dramatic, but misleading. What physics suggests is subtler. That reality could reconfigure, that the rules we experience are one phase among others, that what feels fundamental may be provisional. This does not make the universe less real. It makes it more precise. It replaces mythic solidity with mathematical exactness. And exactness has edges. Those edges are where physics now operates. Not at the center of certainty, but at the boundary of consistency. Measuring, probing, tightening constraints. Not to pull reality apart, but to understand what holds it together. If there is a crack that unravels reality, it is not a single discovery or a single experiment. It is the recognition that the world is held together by conditions, not by necessity. That existence is permitted, not enforced. And that permission has limits. At this depth, physics stops behaving like a catalogue of objects and starts behaving like a set of conditions. The equations no longer describe what reality is made of, but what reality is allowed to do. This shift is subtle, but it explains why so many independent problems now converge on the same theme. The universe appears stable, not because it is anchored to something unchanging, but because it occupies a narrow region, where competing requirements cancel just well enough to hold. This is why precision has become so dangerous. Each improvement in measurement tightens the corridor. Particle masses sit closer to instability. Vacuum energy balances more delicately. Gravity's weakness becomes harder to justify. None of these issues arise because our theories are sloppy. They arise because the theories are too exact. They leave no room for natural explanation. In earlier eras of physics, inconsistencies pointed toward missing ingredients. A new particle, a new force, a hidden symmetry. What makes the current situation different is that adding ingredients often makes the problem worse. New particles tend to destabilize the vacuum further. New dimensions dilute gravity but complicate energy conservation. New symmetries fix one parameter while unbalancing another. The cracks do not close cleanly, they grow. This behavior is characteristic of systems governed by global constraints rather than local mechanics. In such systems, stability does not come from rigidity, but from balance. Remove or alter one element and the entire configuration shifts. The system does not break immediately, but it moves toward a different solution. That language matters. A solution can persist without being unique. It can be long-lived without being inevitable. It can support complexity without being fundamental. The universe we observe fits all three descriptions. It has endured for billions of years. It produces structure, chemistry, life. But it does so by satisfying conditions that appear finely tuned rather than enforced. This tuning is not evidence of design and not evidence of randomness. It is evidence of limitation. The universe behaves as if only a small subset of possible configurations are internally consistent. Most hypothetical universes fail quickly. Some never form stable matter. Some collapse immediately. Some inflate into emptiness. What we inhabit appears to be one of the few configurations that thread the needle. That framing removes much of the drama from the idea of reality unraveling. There is no implication of imminent failure. Instead, there is an implication of contingency. The laws we experience are not guaranteed by logic alone. They hold because they satisfy deeper requirements that we only partially understand. This perspective also explains why progress feels incremental despite revolutionary discoveries. We are not uncovering new layers stacked beneath old ones. We are mapping the boundary of a single allowed region. Each anomaly marks a place where our current description rubs against that boundary. The weight of the particle matters because it tests cancellation. The value of a field matters because it reshapes energy landscapes. The weakness of gravity matters because it hints at missing geometry. The behavior of horizons matters because it reveals informational limits. None of these observations point toward collapse. They point toward constraint. And constraint is the opposite of chaos. It is order under pressure. It is structure that exists only as long as requirements are met. That kind of order can be extraordinarily stable. But it is never absolute. The final mistake would be to interpret this picture emotionally. Fragility here does not mean weakness. It means precision. A crystal is fragile, not because it is poorly made, but because it is perfectly arranged. Small deviations matter precisely because the structure is exact. Reality appears to be built the same way. Once reality is understood as a precise configuration rather than an absolute foundation, many long-standing puzzles fall into place. The universe does not need to explain why it exists in the strongest possible sense. It only needs to explain why this particular arrangement persists. Persistence replaces necessity as the core question. This reframing changes how instability is interpreted. Instability does not imply imminent collapse. It implies accessibility. A system can be metastable for enormous spans of time and still not be fundamental. The vacuum can endure longer than stars live and still not be the lowest state available. Gravity can hold galaxies together and still not be native to the space we experience. Space can appear smooth and continuous while being assembled from discrete informational structure. What physics is uncovering is not a doomsday mechanism, but a hierarchy of descriptions. Each level is valid within a domain. Classical motion works where quantum uncertainty averages out. Quantum fields work where spacetime can be treated as fixed. Geometry works where information density remains low. None of these descriptions are wrong. They are incomplete by design. The cracks appear when one description is pushed beyond its natural range. Particle physics exposes vacuum structure. Cosmology exposes boundary effects. Black holes expose informational limits. Time symmetry exposes the absence of a preferred direction. Each anomaly is a reminder that the framework being used has reached its edge. At those edges, the universe stops looking like a collection of things and starts looking like a pattern that maintains itself. Patterns do not persist because they are solid. They persist because they are consistent. As long as the constraints that define them are satisfied, they remain. When those constraints change, the pattern does not shatter, it transitions. That is the quiet implication beneath the title. A crack that unravels reality is not a tear in space or a collapse into nothingness. It is a shift in what configurations are allowed, a redefinition of the solution space. Reality does not end. It rewrites. Physics does not yet know what governs those deepest constraints. Whether they arise from mathematics, from information theory, or from principles still undiscovered, is an open question. What is clear is that the universe does not rest on an immovable base. It rests on balance. Balance explains why the laws appear tuned. Balance explains why multiple large effects cancel almost perfectly. Balance explains why small deviations matter. And balance explains why understanding advances through precision rather than spectacle. There is nothing mystical in this conclusion. It does not require hidden intention or cosmic narrative. It follows directly from the behavior of constrained systems. When constraints are tight, outcomes are rare. When outcomes are rare, stability feels miraculous, even when it is not. The universe we experience is one such outcome. A long-lived configuration that satisfies the rules well enough to endure. Not guaranteed. Not unique, but real. Recognizing that does not make reality feel smaller. It makes it sharper. It replaces vague absolutes with exact conditions. It tells us not that the world is unsafe, but that it is specific. And specificity always has boundaries. That is where physics now stands. Not staring into chaos, but tracing the outline of what is permitted. Measuring where stability ends. Mapping the edge of consistency. The crack is not something waiting to open. It is the line that tells us how far reality can go.